그럼 본격적으로 에듀케어 리더스 포럼을 시작하겠습니다. 이어서 기조 강연을 진행하도록 하겠습니다. 전 세계 코딩 교육의 기준과 방향을 제시하는 곳이죠. 영국 컴퓨터 협회 BCS에서 기조 연설을 위해서 이곳 에듀케어 리더스 포럼을 찾아주셨습니다. 미래를 바꾸는 소프트웨어 교육이라는 주제로 리 고스 영국 BCS 아카데미 교육개발 총괄 매니저님께서 기조 강연을 해주시겠습니다. 큰 박수로 맞아 주시기 바랍니다.
Ladies and gentlemen, good morning, and thank you for coming along today to see this small talk from myself. My name is Goss, and I'm from the British Computer Society in England. I'm also going to be speaking on behalf of Computing at School, which again is a part of the BCS, the Chartered Institute for IT, and also Barefoot Computing, which is the BCS's primary way of supporting primary school teachers across the entirety of the United Kingdom. So, what's the plan for today? I want to talk about what computing education is for. What curriculum changes have happened in England since 2011? The primary resources that we have available in the UK to support teachers. A little bit about an organization called Computing at School. And finally, to summarize with what we've learned today. So, a quote I like to start with about why we do what we do. Education should prepare young people for jobs that do not yet exist, using technologies that have yet been invented to solve problems of which we are not yet aware. So this breaks down into two sections in my mind. You have skills, so how to use technology, machines, business processes. And then we have disciplines. So we have the fundamental principles that underline computational thinking. We have fundamental laws. We have techniques and methods. Now for skills, there's an issue with teaching these in that they are finite. What we teach in terms of using, for example, a piece of software today won't be the same piece of software those students will be using in 15 years' time. So we have to consider that. A major advantage of the disciplines, those fundamentals of computational thinking and science, is that they date very slowly. Newton's law is very unlikely to change anytime soon. So, what has happened in practice in England? So, we have two subjects. We have information communication technology, which if we go back, comes under skills. So it involved people being able to use spreadsheets. It involved people being able to use word processors. And to use those to be able to automate certain functions. This was predominant and still is predominant across the UK, and its uptake outweighs that of computer science significantly, although we do expect that to change with changes in government policy, which are making it less likely that head teachers will use that, pick it as a subject for their students. What we have is a new subject, which comes under discipline, which does teach those principles of computational thinking. And that's uptake, it's quite small at the moment, but it is growing. And we're hoping to see significant growth over the next few years. And in fact, there was a major announcement in the budget yesterday, which I'll come to at the end of this presentation, which is going to be supporting computer science in the UK. So, what do we want instead of this skills-based curriculum? Ideas as well as technology. We want them to be able to create programs as well as use the programs. We want them to write and produce and not just be able to use. So what we're talking about is a significant change in the expectations for our pupils. But there are significant repercussions, because if we change what the pupils have to learn fundamentally, we also have to change what the teachers are teaching. And that's a big ask, when the vast majority of the teachers in the UK have no professional qualification in computer science, or indeed any IT-related background. So, we've got this brand new subject. To define what the Department for Education said in 2013, a high-quality computing education equips people to use computational thinking and creativity to understand and change the world. Incredibly aspirational. Why is it significant? Because it comes back to that change again from a skills-based curriculum to a discipline where it is the fundamentals of the subject that we are teaching, and they can be applied through time. What you are teaching a 5-year-old will still be applicable when that 5-year-old graduates from university at 21. So, you've heard me mention this numerous times now, computational thinking. And it's a set of skills that lets people break down big problems into their individual components and then put it together in such a way as to solve a problem. So I won't read what's on the board for you. But here's a poster from our Barefoot project. Barefoot in the UK has currently reached 45,000 teachers. And in turn, through this program, we've reached 1.25 million children. We have not gone in and asked the teachers to teach programming. They would run away, they would say, no, we don't want to do it. They're not interested. This program was about introducing computing, not just to the pupils, but the bigger hurdle was introducing it to those teachers that had no background in computing, who, when you go up to them with words like algorithms and decomposition, will back away. So we had to go in a way that would be caring for the teachers as much as it is for the pupils. So the Barefoot program does this by providing resources to teachers that they can teach using the pedagogy that they are already used to. So, if we go through the concepts of computational thinking, we have logic, but it's cross-curricular. You might be asking, why am I suddenly going to talk about art? Well, in the UK, there is a massive time constraint on what the teachers can do with their time. And a vast majority of that time is spent on reading and writing for English and mathematics. So we had to be creative as well about how we introduce computing in a practical manner. So you can teach logic during an art lesson, for example. So I predict blue and red will make purple. Algorithms. For those of you that don't know, algorithms are a set of step-by-step instructions that produce a result, usually a useful one. So you can teach that during cooking, because they have to make a recipe, which is your step-by-step breakdown, and then it produces a result, your baked cookie at the end. Decomposition, breaking down big problems into its individual component pieces. So, labeling the parts of a flower during a science lesson, that would be a bit of decomposition. Phonics. So what is the same about these types of words? Join, boy, boil, toy, floip, soil. You can use that to help pupils identify patterns. Abstraction. So this is about removing the unnecessary detail in big problems. So we have a map of the UK. I need to simplify it because my target audience is X. How can you do that? What are the details you can remove from this map? Do you need canals? Do you need rivers? Do you need motorways? Well, not if it's a walking map. Probably not. Evaluation. So making judgments. I don't know a subject where you can't use evaluation, if I'm perfectly honest. But the example I put up here is you evaluate a gymnastic routine. You identify what's good and bad about it. And then you suggest what could be improved next time you do it. And finally, we have the approaches. So approaches are actually what we consider just to be the fundamentals of good teaching in schools. We have tinkering, which is allowing the pupils to mess around with the problems. We have creating, so designing and making the product. We have debugging, which I'm going to come back to, which is identifying where something's gone wrong and then coming to a solution. And when you're debugging, it can become disheartening. You know, if something keeps going wrong, it's going to get a little bit upsetting for a 5, 6, 7-year-old. So it's also about persevering, you know, keep on going. And finally, working as a part of a group, being able to collaborate with others to come to your solution. So I mentioned debugging there. I've witnessed a number of lessons across the UK, and it's very interesting when I go into a computer science classroom, usually in an IT lab, and you see pupils working with something like Scratch, where they're producing a small program, and they have no fear about it not working. The program doesn't work, oh, no worries, I'll just try this, I'll try X, Y, Z, until they find a solution. There's no fear, they feel very safe in that environment. I've had very different experiences though when I've gone with the same teacher into a maths classroom. And in the maths classroom, there seems to be a general fear about making a problem, about having a problem in your solution. So in maths, there's a great deal of pressure on the pupils to get the solution right first time. And I think if we took some of the approaches that we're singing about in computational thinking and take those over to the maths classes, well, we might see a greater deal of success in those classes. So I've mentioned this very briefly before. Algorithmic thinking. Putting together a set of instructions so that you can get some sort of useful result. Decomposition. Breaking down the problem into its individual component pieces. Generalization. Identifying patterns and commonalities in problem processes, system, solution, data. Okay? But then being able to adapt that and apply it to different situations. Far too often I see students who are perfectly fine working with graphs in a maths lesson. You then go into the computational thinking lab, or the IT lab, whatever you want to call it, and they don't realize that the skills they've just learned in their maths lesson can be applied directly to the programs they're trying to produce in the IT classroom. And I've struggled with this one. I'm not entirely sure why that happens, why they can't take what they've learned here and apply it in other areas. And I actually hope that some research is going to be carried out in the next couple of years into looking at why education has become so compartmentalized in certain areas of the curriculum. Abstraction, reducing complexity by removing unnecessary detail. And evaluation, I'm sure we all know what that is. So, this is one of the Barefoot resources and one of my favorites. And this is the one I use to teach what algorithms are to not just the students, but to teachers as well. So I start off the lesson by going, draw a triangle. Now draw 3 eyes. Now add 3 wings, and so forth. And by the end, all of the people in the room will have these crazy looking monsters, and they will all look slightly different. And then I'll ask the pupils, I want you to design your own alien. But this time, you're not going to draw it. You're going to write down the instructions for what you want to see. And then you're going to give it to one of the other pupils to produce. So, here's an example of one pupil's, and you can see that they've produced two very different results. And that's great, because then we can come back to evaluation. If we wanted to have an efficient algorithm for producing two images that are near enough the same, what do our pupils need to do in order to get that to achieve that result? Well, after a little bit of talking amongst each other, they usually come back with the answer, well, if we want the same result from other people, sir, we need to have more detailed instructions. Great. So they go away. They produce more detailed instructions, and then they share it with their friends again, and again they get someone to draw the first one and the second one, and the result is usually a bit more similar. And from that, we can see various elements of computational thinking. But most importantly, they now know that an algorithm is a simple set of instructions that achieves a result. It's as simple as that. Algorithm, that big scary word that the teachers were afraid of and the students were afraid of, it's not scary anymore. We know it's just a set of instructions. It achieves a result. From this activity, they've also been able to evaluate what they've done. From those judgments, they've made improvements. And they've learned the key thing from our lesson. So, very, very simple activity, but it achieves the result very, very quickly and efficiently. So here we have another example. So this is a program called Scratch. Can I just get a quick show of hands? Who here has used Scratch in their classroom? Okay, so very quickly, Scratch is a programming language based on blocks like this, which the pupils can put together to produce simple programs. Actually, they can produce some fairly complicated programs. So in this example, the student has put together a program which draws a square. And there's actually something very, very difficult here. They have a loop. Most students wouldn't start with a loop. They would just go, move 100, turn 90, move 100, turn 90, move 100, turn 90, move 100, turn 90, to get the result. So the pupil here has actually thought a bit ahead. He's recognized the pattern in his program, and he's applied a solution which is more efficient. So I won't ask you to do this activity. When it comes to testing, here's quite a nice bit of testing. So we have an image on the right, and you ask the pupils to test their knowledge which one of these three programs produces that result. So I'm just going to give everyone 30 seconds to have a think about that. No, it's too mean. I won't test the audience. I'll be sharing these slides at the end on my website if anyone wishes to look at these in a bit more detail. The website, by the way, is Computing at School. So, another activity for identifying patterns and sequences. We have a set of possible numbers. How do we find the next number in the sequence? So the algorithm, multiply the previous number by 2, then add 3 to make the next number. We have logic, because they've had to predict the next number based on the relationship they can see between those numbers. There's the obvious pattern. And the evaluation and debugging here is testing the sequence to see if it worked. And if it didn't, why not? If it did, can we improve upon it? So here we have a finite state machine. So earlier on, I mentioned that there's a great deal of pressure on primary school teachers in England especially to teach English and mathematics. And so it leaves only a very small amount of time for computing. So we cheat the system, so to speak, by slipping in our computational thinking and science into their English lessons, into their maths lessons. So here's an example of a maths lesson. So we have a definite article, an adjective, a noun, a verb, and a connective. And every one of these individual roots through the finite state machine will produce a grammatically correct sentence. So, the old pirate sang, or a huge dog danced. Finite state machines can be used to describe any complicated system. And you can get your pupils to design these for anything. So in my next slide, I've got a very basic example of an ATM machine. Oops. So here you can see an ATM machine. So we enter our card, we enter our PIN, we withdraw cash. Or we can go back to the menu and eject the card. Or we can enter our card, enter the PIN, we can show balance, get card. Sorry. But you get the idea. So we can use these finite state machines to break down complicated systems into easy to describe diagrams. And again, our best teachers are using these as part of their English lessons, science lessons, geography lessons, because they're a beautiful way of describing those complicated systems. So, just a very short note I wanted to share with you. If your pupils work in English at all, the Barefoot resources, which were originally funded by the British Computer Society and the Department for Education in England, are now supported by BT, who have put an amazing amount of effort, time, and money into supporting this, and also by volunteering to going out to schools to share these resources. You can log on to Barefoot Computing, you can get a free account, and there's something like 90 free resources which you can download and share with your pupils and use in your classroom and share with your colleagues. And I do encourage you to take a look. It's all absolutely free, thanks to BT, BCS, and the Department for Education. Another set of resources we have for primary school teachers is Quick Start Computing. So again, we focus our energies on supporting the teachers. So our Quick Start guides provide continuing professional development to support the teachers with their subject knowledge in the classroom. And again, we provide these freely. You can go on to Computing at School, and you can download copies of this for free. Okay, so let's go back to our starting point. So Computing at School formed in 2008. There were concerns about inadequate teaching of computer science. And there were many serious concerns that our students simply weren't engaging with the subject. So 6 years later, we've got a rebrand of the subject from ICT to computer science in England. It is a statutory subject. It has to be taught. We now have a GCSE in computer science for 15 to 16-year-olds. We have tens of thousands of members. Oh, that's a bit of an exaggeration. But we have many, many, many members online, thousands of active members who engage in our forums, who attend hub meetings in their local area, arranged by master teachers and our hub leaders, who are simply volunteers who are willing to put in a bit of effort to support teachers in their locality. And the government is funding Computing at Schools and the Network of Excellence, which is the name for the infrastructure that supports all of this work we do. Computing at Schools come a long way. It started off as literally two men in a pub one evening with a great idea. They started a website, they started to recruit people, and since then it's grown and grown and grown. Their mission, promoting and supporting excellence in computer science via the teachers, not the students. So this is what we believe. Computer science is a discipline like maths, physics, or history. It is a school subject for both primary and secondary school pupils, not just a university subject. It's educationally important. It's economically important. The British government has published documentations that predict that the growth in the technology sector for our nation will be massive. If we're going to have that massive growth, we need people coming out of schools equipped with the skills to be able to go into those roles and those jobs and create those new markets. And those ICT teachers who had no background in computer science, who had no formal computing qualifications, are on the vanguard. They are the ones leading the charge with this new subject. So we have an obligation to do everything we can to support those teachers. So, last week, a major document was published in the UK by the Royal Society, our learned body for the sciences, which advises our government on policy. And they made a set of recommendations about what we need to do with the curriculum, about what we need to do in terms of supporting teachers, in terms of what we need to do in terms of having a national infrastructure to support these teachers. So, stepping back one step, we have these hubs. Like I said earlier, these are just groups of teachers, enthusiastic teachers, who get together voluntarily to support each other. The British Computer Society supplies them with some resources, but at the end of the day, it's up to them to keep themselves infused, to be getting out there, to be helping one another. It's face-to-face. The teachers themselves lead and organize it. We also have online discussion forums, resources. We try to run events regionally through the help of 12 universities that we work with very closely. So how do we build their confidence? Well, that's it. That last slide is how we're building their confidence. We're getting them to talk to each other. So, sorry, I'm going to skip a few slides because I'm looking for this one. So, as I mentioned before, we had that Royal Society report and it made a number of recommendations. Last night at 10:30 p.m. our time, the government announced £84 million of support to provide training for 8,000 new computer science teachers and to create a new national center for computing. The BCS, the Raspberry Pi Foundation, and other organizations that have been talking to the government have been influential in lobbying for them to do this. They've seen the light. They're supporting us, and they're now giving organizations the money that they need in order to train up this new workforce. So, I'll leave it on this note. We've made a great deal of change over the past few years, but we've made a great deal of change for only 20% of the problem. We still have 80% to go. And this is the start of that new wave of making change. And at the very end of the day, it's not the government organizations, it's not the university lecturers. The people making the change are the teachers in the classroom on the front lines. Thank you very much.
네, 우리의 미래인 아이들을 위해서 어떻게 하면 양질의 소프트웨어 교육을 제공할 수 있을지 생각해 볼 수 있었던 의미 있는 강연이었습니다. 감사합니다.